Welcome to this lesson on escape velocity. In this video, we'll explore one of the most fascinating concepts in gravitation, the idea of breaking free from a planet's gravitational pull. By the end of this lesson, you'll understand what escape velocity is, how to calculate it, and why it matters in space exploration. Escape velocity is the minimum speed required for an object to break free from a celestial body's gravitational pull without any further propulsion. Think of it this way. If you throw a ball upward, it eventually falls back down because Earth's gravity pulls it back. But if you could throw it fast enough, it would escape Earth's gravity forever and never return. That critical minimum speed is what we call escape velocity. There are three crucial things to understand about escape velocity. First, when an object reaches escape velocity, it travels to infinity with zero final velocity, meaning it just barely escapes. Second, at escape velocity, the total mechanical energy of the object equals zero. And third, escape velocity is independent of both the direction in which the object is launched and the mass of the object itself. This means a small pebble and a massive rocket need the same escape velocity from the same planet. To derive the formula for escape velocity, we use the principle of conservation of energy. This principle states that the initial kinetic energy plus the initial potential energy must equal the final energy at infinity. At escape velocity, when the object reaches infinity, both its kinetic and potential energies become zero, meaning the total mechanical energy becomes zero. Let's look at the mathematical steps. We start with energy conservation. Kinetic energy plus potential energy equals zero. This gives us 1/2 mv squared minus gmm divided by r equals zero. Rearranging this equation, we get 1/2 mv squared equals gmm divided by r. Notice that the mass of the object, m, appears on both sides and will cancel out in the next step. After simplification, we arrive at the escape velocity formula. V equals the square root of 2gm divided by r here. V is the escape velocity, g is the universal gravitational constant, m is the mass of the planet, and r is the radius of the planet. This elegant formula shows that escape velocity depends only on the planet's properties, not on the object trying to escape. Let's look at some real examples. Earth's escape velocity is 11.2 kilometers per second, or 40,320 kilometers per hour. The Moon, being much smaller and less massive, has an escape velocity of only 2.4 kilometers per second. Mars has an escape velocity of 5.0 kilometers per second, while the massive Jupiter requires a staggering 59.5 kilometers per second to escape its gravitational pull. Let's recap the key takeaways. Escape velocity is independent of the object's mass and the direction of launch. The formula, V equals the square root of 2gm divided by r, is derived from the conservation of energy principle. Escape velocity depends only on the planet's mass and radius. And for Earth, this critical speed is 11.2 kilometers per second. Understanding escape velocity is essential for space missions, satellite launches, and understanding how celestial bodies interact gravitationally.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.